We're in section 13.9. We're going to talk about, our book calls it applications of Extrema. And I think we're kind of, what we're talking about today really is constrained optimization. So all I want to do is go through a couple of examples of constrained optimization, and then we're going to, at the end, we'll talk about a constrained optimization problem that we've all seen or we've all used in one way or another as we went through school, and we can talk about where it comes from too. That's least squares line. So our calculator, when we do a linear regression, we find the least squares line, and we're finally in a position where we can talk about where that comes from, which is kind of nice. All right. So for our first example, we want to we have this surface z equals x squared plus y squared. So first off, what kind of surface is this? Paraboloid, right? So we have this nice paraboloid. And we have a point 550. We want to find the minimum distance from the point to the paraboloid. So this paraboloid, just a quick sketch here. We have a paraboloid on the z-axis. So here's our paraboloid. So and we have a point here, 550. And we want to minimize this distance, whatever, there's some point on this paraboloid that's going to minimize the distance from the point to the paraboloid. All right, so we're minimizing the distance. What function are we trying to minimize? What is the distance between 2 points? We need to represent our distance as a function. Distance between points in space, square root x minus x0 squared plus y minus y0 squared. We're using the distance formula, plus z minus z0 squared. Where the point that we're interested in is x0, y0, z0. So this is the function that we're trying to minimize. We need to minimize d. Subject to the constraint that z equals x squared plus y squared. So that's our constraint. So on the paraboloid, we're going to use this. So right here we have a function of 3 variables. We're going to use our constraint, z equals x squared plus y squared, to reduce it to a function of 2 variables. So on the paraboloid, we can say x equals x, y equals y, and z equals x squared plus y squared. So our distance, the function that we're trying to minimize, is d equals the square root of x minus 5 squared plus y minus 5 squared plus and our z value is 0, so minus, 0 minus, I'll write that in, 0 minus x squared plus y squared. Squared. So no, our z, yes, yes, should turn it around. X squared plus y squared minus 0. Doesn't really matter, but just to be consistent. I can get rid of that. All right, so here is the function that we're going to minimize. What do we want to do here to simplify our work? We've talked about this in several different contexts this year, when we want to minimize this function. So I don't want to deal with this square root. So we can minimize the inside, minimize the square of the distance. So we're going to minimize. Our distance is going to be minimized when what we have in here. So we're going to minimize x minus 5 squared plus y minus 5 squared plus x squared plus y squared squared. So that's what we're going to minimize. So now we have something that we know how to work with. We have a two-variable function. We want to find a minimum value. So we're going to take our first partial derivatives, set them both equal to 0, and we could use our second partial test. We're going to use think about geometrically what's going on here to make sure that we have a minimum. All right. So is everybody clear what we've done so far? We're minimizing our distance function, and we used our constraint. This paraboloid is a constraint on our problem to eliminate one of the variables in our distance function. All right, so I'm going to switch pages. We're going to minimize this quantity. So our partial with respect to x of our and I'll call this. I'm going to call this D, capital D, for the square of the distance. So we're going to minimize this function. So partial derivative with respect to x of D, we get 2 times x minus 5 plus, when we take our derivative of that quantity, I get 2x squared plus y squared, and we take the derivative of the inside, equals 2x. And I can simplify that. I get, when I expand this out and simplify, I get 2x minus 10 plus 4x times x squared plus y squared. And we take the partial with respect to y, and we get, when we take our derivative, to y minus 5 plus 4y, similar derivative, 4y times x squared plus y squared. And when I simplify that, expand and simplify, I get 2y minus 10 plus 4y x squared plus y squared. So we're going to set each of these equal to 0. So we want dx equals the partial with respect to y. We want that equal to 0. So I get a system of equations. When I set these equal to 0, I'm going to write this, and I'm going to call this equation 1. For equation 1, I get 2x plus 4x to the third plus 4xy squared equals 10. And for equation 2, I get 2y plus 4y to the third plus 4x squared y equals 10. And we need to solve this system of equations. So what are we going to do to solve this system? How can we simplify this? Any ideas? Let's set them equal to each other. We end up with x cubed and y cubed and then xy squared and x squared y. It ends up kind of messy. Anybody see a way that we can? I want to eliminate something. I want to get rid of stuff. Anybody see what we can do here? That we can use elimination and get rid of some of these terms. So we want to subtract one from the other. The problem, the way it sits right now, is I have a 2x and a 2y, a 4x cubed and 4y cubed, and a 4x y squared and a 4x squared y. So multiply. So Jason says multiply by xy. So that, I think that would work. The idea that I had was, let's multiply the first by y. And multiply 2 by x. And then subtract. So when I multiply 1 by y, I get so I'm going to multiply the first one by y, the second one by x, and the other thing that I'm going to do as an intermediate step is I'm going to divide everything by 2, because we have a factor of 2 here, and I'm going to divide everything by 2. Just to get rid of the factors of 2. So when I do that, I end up with xy plus 2x cubed y plus 4xy cubed equals 5y. And for the second equation, I get xy plus 2x y cubed plus, sorry, this should be a 2 when I divide it by 2. 2x cubed y equals 5x. And now I'm going to subtract. And when I subtract, thankfully, I get 5x minus 5y, sorry, 5y minus 5x equals 0. And this tells me y equals x. And I think your method would have worked as well. I think you would have ended up in the same place.
I think it was on a similar line of...
Right. Right. Oh, you said multiplied by
No,
xy, and you meant 1 by x and 1 by y?
Yeah.
Okay.
That's the way I was looking at it, but I
Okay.
came out differently.
No worries. I think you were thinking, like you said, you're thinking the exact same thing. All right, so we get y equals x. Now I'm going to substitute into equation 1 for y. So I'm going to substitute this into equation 1. And I get and I'm substituting in here, and I've divided by 2. I'm dividing this by 2. So I get x plus 2x to the third plus another 2x to the third equals 5. So this tells me that x plus 4x to the third equals 5. I'm going to factor x times 4x squared plus 1 equals 5. And the reason I factored is I'm hoping that we can look at this and pick out a solution without having to solve this equation. Anybody see it? Can we pick out what we call by inspection without having to solve the equation? X equals 1. X equals 1 is a solution. So that's a nice solution. I plug this into my equation and I can solve for y. So plug in x equals 1, divide this by 2 again, plug x equals 1 in there, and I end up with 1 plus 2 plus 2y squared equals 5. So I'm substituting that into equation 1 after I've divided by 2. And this gives me that y squared equals 1. And finally we get y equals plus or minus 1. And then let's go back and look at our graph. If x equals 1 here, is it going to make sense that y equals positive 1 or negative 1 to give us a minimum distance? What's that?
It should be the same.
So if y equals negative 1, we're over here on this side of the paraboloid. So our distance is over here. So it's going to make sense that x equals 1. We could also substitute this back into equation 2. Substitute into equation 2 when x equals 1 and verify that y is going to be positive 1. So I can say substitute into 2, and we see that y equals 1. So we have x equals 1, y equals 1, and finally, what does that tell us z equals? Z equals 2. So we get x equals 1, y equals 1, z equals 2. And we wanted to minimize the distance. So our distance, finally, is the square root of 1 minus 5 squared plus 1 minus 5 squared plus 2 minus 0 squared. And we simplify that, and we get the minimum distance is 6. 6 is good. So for this one turned out nicely because we could solve this by inspection. We could also, otherwise we would have to if I were to give you something like this and we had to find a solution to this, and it wasn't easy to pick it out like this, we'd have to maybe graph it in a calculator or something like that to solve this equation for x. All right, so there's one example of a constrained optimization problem, minimizing the distance from a point to a surface. The distance is our function that we're minimizing, and our surface is a constraint. We can use the constraint to reduce the number of variables in our system. And then we had to do a little bit of work on our system of equations. All right, questions there? It's kind of a fun problem. All right, let's look at another type of problem, constrained optimization problem. So we want, for this one, we want 3 positive integers. X, Y, and Z. such that the sum is 32. And for some reason, we want x, y squared, z is a maximum. So we want to find these three numbers that add to 32 such that x, y squared, z is a maximum. So our function, we're trying to maximize x, y squared, z. So f of x, y, z is x, y squared, z. We want to maximize that. And our constraint is that x plus y plus z has to equal 32. So what I'm going to do, just like on the last one, I'm going to use the constraint function, the constraint condition, to reduce the number of variables. Because here I have three variables, and we haven't talked about how we minimize a three-variable system. It's a similar process, but it's a lot more work to minimize a three-variable system or three-variable function than a two-variable function. So we'll use our constraint condition to reduce our number of variables. So from our constraint, we get z equals 32 minus x minus y. And we're going to plug that into our function. So f is x, y squared times 32 minus x minus y. And we're going to minimize this function. So let me expand this out so we get 32 xy squared minus x squared y squared minus xy to the third. And we want to maximize that. I think I said minimize before. So we want to maximize that. So we're going to do our same procedure. Take the first partials, set them equal to 0, and solve our equations. So we want our first partial with respect to x, f sub x. We take our partial derivative, and we get 32y squared minus 2xy squared minus y to the third. And we want that equal to 0. So let's work with this one first. So what can we do with this one? Let's try to pick out some numbers here. Factor a y squared. So I get y squared times 32 minus 2x minus y equals 0. Do we want y equals 0 as part of our solution? No, Dylan says no, because if y equals 0, what's this product? 0, and we hope that 0 is not the maximum. And 0 is not a positive integer, right? 0 is not a negative integer either. So we don't want y equals 0. So y is not equal to 0. So we've made our system of equations a little nicer. So we get y equals 32 minus 2x. That's a little easier equation to work with. Now let's work with a partial with respect to y. And hopefully we can do something similar with that. So a partial with respect to y. When we take that partial derivative, we get 64xy minus 2x squared y minus 3xy squared, and that equals 0. And what can we do with this one now? Factor out a xy. So I'm going to take out an xy. And when I take out an xy, I get, what do I end up with? 64 minus 2x minus 3y equals 0. And we said we don't want y equals 0, and we also don't want x equal to 0. So we end up with 64 minus 2x minus 3y equals 0. And we know that y equals 32 minus 2x. So we're going to substitute that into this equation, and we can solve for x then. So I'm going to substitute y equals 32 minus 2x. So I get 64 minus 2x minus 3 times 32 minus 2x equals 0. And I can solve that, simplify that, solve that for 0. When I do that, I end up with x equals 8 when I solve that equation. So x equals 8. I use y equals 32 minus 2x squared, and I end up with y equals 16. Substituting that back in there. And finally, z, because x plus y plus z has to equal 32, I get z has to equal 8. So those are my 3 positive integers that sum to 32 and maximize x squared plus y squared plus x y squared z equals a maximum. So another type of constrained optimization. Questions there? So tomorrow we'll learn another technique for working with these constrained optimization problems that in some cases it's a little less, it's less work, and it's kind of nice because it involves a group. All right. What I want to talk about next is just this idea of constrained optimization. Lets us see where a technique that we've used a lot, that our calculator does for us, we can see where this comes from. And this is what we call the least squares line. So for the least squares line, what we're doing is we're fitting a line to a set of data. So we have data points. We have data points, and I'm going to do, we have a set of data points. x1, y1, x2, y2, x3, y3, etc., dot, 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 up to x n y sub n. And what we want to do is we want to fit this with a line some line y equals f of x, some linear function. Fit with a line y was f of x. So we're graphing our data points, and we want a line that matches them as well as possible. So I'm just going to draw this up here. Let's say this is x1, y1. Let's say this is x2, y2. And I'm going to keep going. And, well, let's say here's x3. I'll stop with 3, y3. And we want a line that matches these points as well as possible. So we're fitting a line to those data points. One way to do this is to minimize the square of the distances. So if I draw the distances from these points to this line, I'm going to call this D1, D2, D3, one way to fit this line is to minimize the squares of these distances. So there are other ways to come up with the equation of the line. But we want to minimize the squares of our distances. So if we minimize the squares of the distance, kind of like we did with the parabola problem, we minimize the square of the distance, that's going to minimize our distance, but then we don't have to worry about that square root. So we minimize the distance of those squares to that line. That's one way to fit that line to the curve. So what we are minimizing this S, we call it S, the sum, that's going to be the sum, I equals 1 to n, of f of x sub I minus y sub I squared. So we're minimizing the y values from the points to the line. And this should be an I, y sub I. And we know that f is some line ax plus b. So our sum then is a function of a and b. S is a function of a and b. So that distance is going to be affected by the value of a and b. Well, there's a two-variable function. We want to minimize that sum. So we can use the techniques that we've been talking about to minimize this function of two variables. So what we do is we take the first partials with respect to A and the first partial with respect to B, set them equal to 0. We run our second partials test to ensure that we have a minimum. Now the hitch is that this function is a function of A and B. It's also this sum. So it gets extremely messy. So what we end up with is that if we minimize this function with respect to A and B, so we have a two-variable function. This f is ax plus b. We minimize s, this multivariable function. We get that A equals n. That's the number of data points we have. The sum I equals 1 to n of x sub I, y sub I, minus the sum I equals 1 to n x sub I, sum I equals 1 to n y sub I, divided by n, sum I equals 1 to n x sub I squared, minus sum I equals 1 to n x sub I quantity squared. That's our A. That's how we find our A. That gives us the minimum value. And B, luckily B is a little simpler. B is 1 over n. The sum I equals 1 to n of y sub I minus A sum I equals 1 to n of y sub I. Or sorry, x sub I. And y equals ax plus b is the least squares line. All right, so finally, halfway through Calc 3, we have developed the procedures. I'm not going to make you guys do this, but we've developed a process where we could find analytically, if we had to, this A and B that gives us our least squares line. It comes from minimizing a two-variable function using partial derivatives and the second partials test to ensure that we have a minimum. So finally, after however 3 years of calculus, we can find the least squares line that your calculator will do for you in half a second. So thank goodness for calculators. So the reason I talked about this is that it's a very concrete example of what we use optimization for, how we would use first partial derivatives, second partials test to do something that that we've used. Basically, I know that I was talking to Miss Sharrow next door. She taught least squares curve fitting in Algebra 1. So something that you learn most students learn as freshmen in high school. Now finally we've got the tools that we could use to develop this line. So just kind of an interesting application of partial derivatives and optimizing to multivariable functions. All right, homework. There we go.